Have you ever struggled to expand your AI training dataset without collecting more data? In this video, we'll explore the Torchvision library, focusing specifically on image transformations. By mastering these techniques, you can pre-process and augment your images, boosting your AI model's performance without the hassle of gathering extra data. We'll start with the dataset from Hugging Face, feed it into PyTorch's Torchvision library, and dive into hands-on analysis, all done in Python. Starting with a fresh Google Colab notebook, we'll import our dataset. While we could use the Hugging Face libraries, we'll opt for pandas due to its versatility, using the read CSV method with the dataset's URL. Let's grab a dataset from Hugging Face. We'll select one of the most popular datasets, the Amazon product descriptions. This derived subset includes product names and, crucially for us, product images. These images will be perfect for demonstrating image transformations in machine learning. Using pandas, we'll import the dataset via the provided URL, loading all 10,000 rows of training data. Before proceeding, let's check our hardware resources to ensure we're within limits. Fortunately, at around 20 megabytes, the dataset should fit comfortably into RAM. Now, let's dive into the data frame. We'll extract the values and examine the first record. It includes columns like ID, name, and images, though the images are links, not embedded data. These columns correspond to our data's table rows, including unique IDs, product URLs, variants, and more. Suppose we're crafting a new PyTorch dataset from this data frame. We'll use torch_utils data to obtain both a dataset and a data loader. By creating a product dataset class that inherits from PyTorch's dataset class, we'll define several essential components for this subclass. First, we'll fetch each image from its link and convert it into pixel values, storing these in a new product image column. Let's assume our training labels are the selling prices. We'll attempt to predict price based solely on the image. This requires normalization, and if we use a convolutional neural network, we'll need to reshape our data appropriately. Finally, we'll set up our input X and output Y attributes. To complete our PyTorch dataset, we'll need to implement a few more methods, starting with defining getItem. With our product dataset class defined, we're ready to instantiate it. We'll set a batch size of 32. To avoid duplicating column names, we'll name our image data column product image. While parallelization could speed things up, we don't want to overwhelm our notebook resources or burden the server hosting the images. Instead, we'll simplify by sequentially compiling a list of images. Downloading all 10,000 images might be time-consuming, so to illustrate the process efficiently, we'll work with a subset. Let's sample 100 images from our data. It looks like we'll need to reset the index when creating our sample dataset. Since we're mixing our processing types a bit, let's convert to float at the beginning and use from NumPy for our x values. The images come in various sizes, so to keep things tidy, we'll resize them all to a consistent 224 by 224 pixels. This uniform size will be especially useful if we decide to use a convolutional neural network approach. Our labels or y values are currently strings, so we'll want to convert these to floats as well. After some pre-processing to remove the $sign, we can smoothly convert them to float. Now we're finally in good shape. Let's take a look at the new dataset we've created. We have our x values, the images, and our y value, the price, like $29.80. The tensors for the images might look a bit odd. They're 224 pixel by 224 pixel images with 3 channels. Let's do a quick check to ensure the images are looking good. We'll convert them to NumPy arrays and view them using matplotlib. The images seem fine. There's some white in the corners on the test image, but they're loading nicely. Now here's where things get interesting. We can perform some data augmentation. By importing the Torchvision library and its transforms module, we can generate more data by performing random crops on our images. We'll define this in transforms compose so we can combine several transformations and apply a random resized crop. We'll set some scale and ratio parameters for the crop. However, it seems our batch dimension might be causing issues. While we can access our individual image, we need to address this. The problem might be that we need to specify the number of channels in our image since we're dealing with RGB images without transparency. It appears we have a formatting issue. Our batch size is the first dimension, width and height are the second and third, and then the channels come in at the end. This issue arises because it expects a different order, channels first, followed by height and width. We'll need to reshape this a bit. After fixing our tensor dimensions, we can see the result of the random crop. The idea here is that we're creating richer data by making small random crops on the images. For example, on the left, the wing of this dragon product is partially cropped. Given the complexity of handling the dimensions of our tensor, including batch and channel, we might want to perform the permutation earlier in our dataset. This way, we can avoid reshaping before our transformations. Essentially, we'll integrate these permutations directly into the dataset, applying the operation on the X tensor directly. So there we have our original image, and there's our crop. Note that we can run this a few times and you'll see varying portions of the image are cropped. We can, of course, change the cropping by changing the scale value, which will enable potentially much more aggressive cropping. Let's look at some other example transformations that we can use to potentially augment our data. For an image like this one of the dragon, for example, we could probably do something like a horizontal flip. Note that because we have this random aspect to it, it's only going to do this randomly. So now we've got a flipped version of our dragon, and we can, of course, combine these as well to give us some random cropping and also occasional horizontal flipping. Another good one to keep in mind is random rotation. Let's rotate, for example, by up to 15 degrees or so. You can see that that has shifted the entire image. We can also specify a fill. Since we know that this is a white image, we can use that for our fill, specifying it as 255, 255, 255 for the fill. Now that looks a little bit more natural. Again, let's combine that with everything else here, and we start to get quite the variance for our dragon. This could potentially be used to create dozens of additional images per source image that we have. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include all code and the diagram file in the description as well. If you have any questions, please post them in the comment section and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy responsibly.